Okay, so conduct and interpret a simple linear regression. So now that we've estimated the parameters, we have to test them to determine if they're statistically significant or not. So I'm super excited about this because this builds upon a lot of what we learned about in Chapter 9. So let's think about this. If the slope is 0, then there is no relationship between x and y. So this is a figure we saw earlier on in the chapter, where it's showing that the slope is 0, meaning that, right, the slope is 0. There's no change in it. So as x increases or decreases, what happens to y? Nothing. So it's basically saying, hey, x, in terms of student population size, if it's big, if it's small, no matter what it is, it does not affect sales. So in this case, there would be no relationship between x and y. So that is basically, you can kind of think about that as the null hypothesis, that there's no relationship between the two variables, right? The null hypothesis means 0, no. So this is a good example of the null hypothesis saying that, there is no relationship. So we want to test that. We want to test that because if we find that basically the slope does not differ statistically from 0, then we basically can say that x is not related to y. But if it is statistically significant, meaning that the slope does differ from 0, that means that as x changes, y does change too. So that's what we're going to do. We're going to test for a significant regression relationship. We can conduct a hypothesis test to determine whether the slope parameter is 0 or not. So we can use two tests. Right now we're going to talk about the t-test, which, hey, we've seen before. So what do we do in hypothesis significant testing? The first thing we do, right, we state our hypotheses. So our null, right, is that parameter, the slope parameter b1 is equal to 0. The alternative, it's that it's not equal to 0. So again, we estimate this beta 1 with b1. So this is what we're going to do in terms of looking at, in terms of like the sampling distribution and all that. So let's slow down and go back to Chapter 9, where we learned all about hypothesis significance testing. So remember, right, we learned from Chapter 9, this is actually slide 18. Do you remember when we were talking about the coffee example where the coffee cans had to have at least 3 pounds in them? So what we did, right, was we had a z-test, right, a test statistic. We had a z, and we compared the average, right, the point estimator, and the point estimate 2.92 from 3, which was the population parameter, right, 3 pounds. That's how much it had to be filled with. And then we divided that by some standard deviation. So this was the standard deviation of the sampling distribution, which is a standard error, right? And we calculated that by dividing the, right, sigma divided by the square root of n, right? And then we plugged that value in here, and we were able to calculate some type of test statistic which we could use to calculate probability. So let's go back to our example. That is exactly what we are going to be doing, just with minutely different equations. So again, we're interested in a t-test, right? Because a lot of times we don't know, like the population, standard deviation, things like that. We have to estimate it. So remember, when we use the z-test, the population standard deviation was known. We don't know it in this case, so we're going to have to resort to using the t-test, which is okay. We know how to do that already. So you'll look at the equation. It's very similar to the z equation we just saw, right? It's the difference between some point estimator and some population parameter divided by a standard deviation, right? We have our point estimator, we have beta 1, which is 0, right? We're testing to see if this estimate is statistically different from 0, and then we're dividing it by some standard deviation, right? So essentially it boils down to beta 1 divided by the standard deviation of beta 1. So again, to calculate this test statistic, we need the standard error, right, which is the standard deviation for the sampling distribution for beta 1. We already know that, right? The standard error is the standard deviation. What is the standard deviation of? A sampling distribution, in this case B1. That's what we're interested in. So before we go forward with this equation, I just want to point out that this value right here, this equation for t, remember when we have test statistics, we can use that critical value approach where the larger our test statistic is, the more likely we are to reject the null. So how would we get a large t value? Well, either our slope estimate is very big, right? It's different from 0, or or, right? This value here in the denominator is small. Well, what is this? It's an error value, basically. So the smaller the variability in the error, right, then the more confident that we can be in this estimate here. So that would also increase t. So again, this coefficient, if it gets larger and or if the standard error gets smaller, t gets bigger. A larger test statistics mean we're more likely to reject the null. So in terms of, again, conceptually just thinking about like your test statistic, right, if your parameter estimate really is different from 0, right, and it's bigger, it's larger, it's saying that there is a larger effect basically of x on y, so we're more likely to reject the null hypothesis. Also, if we have less variability, less error, right, that's going to help too, because we have more of like a precise measurement, if you will. So let's get back to this equation, right? So to solve for t, we already have b1, right? We already estimated that. What I think that was 5. So we already have that. So now we have to figure out what the denominator is. So let's look at this a little bit. So this is, right, our standard deviation, right? So we have that equal to this, but remember this population standard deviation, sigma, we do not know what it is. We have to estimate it. So when we estimate it, what do? We use the sample, and the sample estimate is S. So we have to estimate that, and that will be able to give us our SB1. Also, the denominator in this, we're used to seeing the square root of n, but this we've actually seen before. What is that? Do you recognize that? Right, that's just taking our x values and finding the difference between the mean and squaring it, right? We've already actually calculated that, right? That was 568. So we calculated 568 back here somewhere. As I'm scrolling through. Yes, 568. We calculated this already. So we already have that value calculated. So that's good. So we already have that that value. Sorry, let me scroll through. So we have that. So we just have to get a value for S, right, which is the estimate of the standard deviation, right, the sigma, the population. So we have to be able to estimate that. So in terms of our equation, what's it looking like, right? We already know we have an estimate of this, 5. So in terms of the standard deviation, right, the standard error, the standard deviation of B1, right, it's equal to S divided by the square root of 568. So now we just need to solve for S. We need an estimate of the population standard deviation, right? S is the estimate of the population standard deviation. So how do we get that? Okay, this is where we need to take a deep breath and kind of think about another concept, but it's related. So remember E, epsilon, it's the error term. It is a random variable. Remember, random variables have distributions with a mean and a variance, right, sigma squared. So we need to estimate sigma squared, right, because we don't know it. We can estimate it, right, with S squared. So if we can estimate it with S squared, we can just take the square root of it to get S. So we're getting closer. We know we kind of have to figure out what this value is. So let's think about what this value is. What is sigma squared? It represents the variance of epsilon, the error term. We already talked about that. But it also represents the variance or the variability of y, right, and of the y values around the regression line, right? Well, we already have that, right? Remember when we're talking about our y values, right, the observed values that we have and the predicted values. The predicted values are the ones that fall on the regression line, right? Remember what those are called? Those are the residuals. Those are the deviations, right? So those deviations of y around the regression line, they're residuals. And we already have a measure of the residuals. Remember, it's the sum of squared errors. So the SSE, the sum of squared errors, represents the variability of the observations around the regression line. Great. So basically, we can use that to estimate s squared, and if we just take the square root of that, we have s, which is what we need. So the only thing we have the last thing we have to consider is that every sum of squares has a degrees of freedom associated with it, just like the t distribution. Remember, each t distribution has its own individual distribution based off of the number of degrees of freedoms it has, which is just based off of the sample size. So what are the degrees of freedom for the sum of squares? Well, for us, it's n minus 2. So it's n, our sample size. Again, so sample size is related to this, but it's 2 because there's two parameters we're trying to estimate, right? What are they? Right, the slope and the y-intercept, right? The y-intercept and the slope, to read that correctly. So the value, the sum of squared error divided by the degrees of freedom, it does provide an estimate of, right, sigma squared, which is what we need, because if we have an estimate of this, right, we'll get s squared, and then if we just take the square root of it, we'll have s, which is what we need. So this equation, the sum of squared error divided by the degrees of freedom, is called the mean square error, the MSE. So again, the mean squared error is equal to the sum of squared error, right, divided by its degrees of freedom, which is n minus 2. That gives us s squared, right, an estimate of sigma squared. So if we just take the square root of the mean squared error, right, we're going to have s, which is what we need. So let's do this, right? We already have the sum of squares error. I think I've done this. Have I done this yet? In Excel, maybe I didn't. So we have the sum of squares error, which we already calculated. Sum of squares error. Do I have that in here? Now I can't remember where I put this. Okay, so let's go back and just find that. The sum of squares error. Okay, it was 1530. Where was this? Oh, okay, yeah, I highlighted it. So yeah, the sum of squares error, right, we have that value that we already calculated, right? This is the squared error, so if we just sum that, we have the sum of squares error, so it's 1530. So we have that. Let's go to our t calculations. So if we want to figure out what s is, right, we need to take the square root of the mean squared error. So that's going to be equal to the square root of the mean squares error, which is 1530, and then it's divided by the degrees of freedom, n minus 2. So we have 10, right, because that's n, our sample size, minus 2, and then we hit enter. So that is actually our s value, right, our estimate, right, of the population standard deviation here that we have. So we have that. So now we have all the values that we need to be able to calculate SB1. So remember SB1, right? So this is the value, right, when we're looking at the big picture, right, we're trying to calculate our t statistic, right? This is just B1, 5, which we already estimated, minus the null, that it's 0, divided by SB1. So if we need SB1, right, we needed S, which we just calculated, and we got to divide it by this value right here, which we had already calculated, which I said before, which was the square root of 568. So we have this value we calculated just now divided by the square root of 568, right, and we get 0.5803. 0.5803 with some rounding, right? So now we can calculate our test statistic, right? Our test statistic just is 5 divided by SB1, and we get 8.62 with rounding. So that's actually a pretty big t value. Usually somewhere around t is 2. Somewhere around that value is significant. So if we know it's 8 point something, this is highly likely that we're going to reject the null. So what do we do to find our p-value? Right, we use the t distribution because that's what we're working with. We use that function, and it takes 3 arguments. It wants x, which is our t-value. It wants the degrees of freedom, which is, right, 10 minus 2, which is 8. And then the number of tails, we're going with a 2-tailed test, and it gives us 2.55 to the negative 5. So that's 0.0000 0.25, blah, blah, blah. So it's less than 0.05, it's less than 0.01, it's less than 0.001, so we reject the null. And so basically what we're saying by rejecting the null is we're saying that that slope estimate of the parameter is statistically significant. It is statistically different from 0. So therefore, yes, x does have some type of association with the outcome variable y.